this is a self-healing approach. So there have been many approaches to self-healing concrete. One is autogenous healing, which is basically using the things that are already inside concrete. And the other ones are use of external substances like mineral admixtures, like other agents and some bacteria. So my research is focused on autogenous healing only. And in that, there are two basic mechanisms. One is physical and one is chemical. So in the physical causes, as you can see in this image, it's basically through blocking of external particles or broken particles that allow the crack to be sealed. But in terms of chemical causes, there are basically two main causes. One is continued hydration of concrete, and the other one is carbonation. So among these, I have delved deeper into carbonation. So in carbonation, basically it has been reported as the major autogenous healing mechanism, and it is limited by currently the carbonation which happens atmospherically by itself. It's limited by amount of dissolved CO2 from the air outside, and also a lack of lime, like calcium hydroxide in concrete. Uh, and high pH is suitable for the precipitation of calcium carbonate, but a system of carbonation is not able to maintain a high pH because of the following mechanism. As you can see, while carbon dioxide from the atmosphere is dissolved, there are two hydrogen ions released, and this leads to a lowering of the pH. And so basically, the pH lowers and it slows down this process in itself. And also, with a lowering of the pH, we can get an early initiation of corrosion in concrete. So that's why, as you may all know, that carbonation is not favored uh, in concrete for durability. And then in autogenous healing, so there are some advantages to it, like it's less expensive, there is no extra expensive materials needed. There is a limitation that water is needed most of the times for healing. Some studies have reported that even up to 95% of the relative humidity, there has been no healing of cracks. And so carbonation, in terms of carbonation itself, it stops after 4 to 5 days, because the natural carbonation, in natural carbonation, carbon dioxide is not able to diffuse to the cracked locations and support healing. And also the pH of concrete decreases, which leads to depassivation of the protective film and initiation of corrosion. So these are the limitations as of now. And in terms of the comparison of the two mechanisms, I would like to just give you an overview that carbonation has been reported as to contribute up to 80% of the healing, and the rest 20% roughly comes from continued hydration. So I'm just going to skip this. And so there is some improvement needed in carbonation though, because as you can see in natural carbonation, only the surface usually gets to dissolve carbon dioxide and precipitate. So there is very less precipitate inside the like in deep inside the crack, and more precipitate on the surface, and this blocks further diffusion of carbon dioxide inside. So you rarely can fill a crack using just natural carbonation. Um, and as we have seen before, it decreases the pH in itself. So my proposal for improved carbonation using sodium carbonate is basically just providing carbonate ions directly without getting a dissolved carbon dioxide from outside. And this will this should react with calcium hydroxide to increase the alkalinity and as well as produce calcium carbonate. So this time we are not reducing the pH, we are actually increasing it. So this should support the precipitation as well as should prevent corrosion from happening. And also it should, since sodium carbonate is now inside the matrix, it should be able to heal cracks from inside as well, not just from the surface. And this was one previous study that has been done in this regard. So they basically introduced sodium carbonate uh, ions as internal inside the porous aggregates, and then they added a lot of other things as well. But basically, in their study, they microscopically showed that there is an existence of precipitate at deeper depths in cracks, not just at the surface. So in my analysis, I have conducted the following laboratory tests for a quantification of healing. So one is recovery in compressive strength, in split tensile strength, and recovery of damage due to shrinkage, recovery of bond strength, like by using fiber pullout, and recovery of permeability of concrete when a stress is applied. So in terms of split tensile strength test, what I did was first of all, I tested 5 cylinders up to their ultimate strength, so as to know what is the ultimate load at which it's failing. And then I tried basically different percentages of loading, and I found 90% of the ultimate load is able to induce some damage uh, for split tensile measurements. And then I assessed the damage on the same day, and then allowed them to heal under different conditions, and then I tested them again. So this is what I did for selection of like preloading level. So you can see that first I tried at 60% of ultimate loading, and roughly there is no difference in these values. At 80% also there is no difference. It might be a slight increase, but there is a standard deviation here that contributes to it. So at 60 to 80% of preloading, in terms of split tensile behavior, it's not showing a damage. But when I preloaded at 90% of the load, uh, you can clearly see that there is a damage. It's about 12% of the damage. And it's on the same day if I repeat the test after doing it for once. And this is after healing. So the first bar is basically the initial test to quantify the strength. This is the repeated test on the same day. And this is the samples that were damaged up to 90% and then reloaded, and reloaded after 3 days of curing. And so they have a higher strength. And then this is water and this is air. So we can observe that sodium carbonate is able to enhance this split tensile strength uh, after damage, and water is also performing better than air. And overall, in 3 days, the all of the samples improve their strength up to a little bit. So this was one conclusion that I could draw from split tensile tests. Then this is self-healing of cracks caused by early edge evaporation. So the thinking behind this is let one batch of samples. Uh, I subject them to a constant flow of air for a specified time period, and the second set I covered them with plastic sheets, so they are not subjected to evaporation at all. While one is under a constant flow of air for a specified time period, which is I usually took 1 or 2 days as this time period. And after this, I took out both samples and I tested them in compression to evaluate what damage this difference has done. Uh, so then after that, after I have evaluated the damage, I again put them under 3 different conditions and reevaluate what the strength becomes. So this is a compressive strength of mortar. And so here in this graph, we can see all of that data. So basically, first of all, we have two branches. One is which is this one has been covered all the time, and this branch has been subjected to evaporation through the first 2 days. And in the first 2 days, we can see that there is a decrease in strength if we leave the samples under a constant flow of air. And this difference, like this is an average of 5 samples each on both, and uh, so this difference was roughly 30%. So there is a 30% loss in strength if we don't cover our samples and leave them under a constant flow of air as well. So this difference is present at 2 days. So this is the damage part. And then I leave them under different conditions of healing. So since it is early age, so there is continuous hydration going on, as well as the extra curing that we are providing. So as we can see in both the cases, there is a rise in strength over age. And so this is the difference between sodium carbonate and water healing. So as we can see, if we subject the sample to sodium carbonate, it is having a higher strength. Even in this case, it is having a higher strength. To calculate some percentages, uh, I did this calculation. So there was a difference in of 30% at 2 days. In this case, there was a difference of 30% in water healed samples. So basically, this one and this one, there is now a 35% different post curing, and in sodium carbonate healed samples it's a difference of 25%. So we can say that sodium carbonate has helped reduce this loss of strength in the early age, as well as we can see that it's definitely performing better than a water curing. And similarly, that was for mortar. Then I did the same test again for concrete. In concrete, the the results were not so starkly different. So I observed a loss of around 10% of strength at uh, after even 3 days of exposure, and after curing for 7 further days, uh, while we can see that sodium carbonate healing is performing better in this one as well as in the covered samples, but overall the damage itself is not that much in concrete. So in concrete, since there are internal curing as well, and since there are aggregates as well, it might help reduce the shrinkage coming from a constant flow of air. So these are just some numbers that I calculated for the difference in the healing conditions. And so that was a shrinkage loss on concrete cylinders. In this test, I tested the bond between like steel fiber and concrete. So there are basically two methods of assessing the damage. There are two techniques of introducing damage into the system. Once again, I can leave these dog bone specimens with one fiber in between and leave them under a constant flow of air and assess the damage again. Or I could now preload the samples up to a certain value of fracture energy so as to produce a similar damage in all of those samples, and then this can be introduced as a damage, and then they can be tested again for self healing. So basically the rest of the healing part stays the same. One will be submerged in water, one is sodium carbonate water. So this is the assessment of damage due to cracks from evaporation. So after 1 day of demolding, I leave them for one more day under a exposure of constant flow of air. And then these are basically 6 samples tested each. And I compared the peak load and the energy under the curve. So in both the cases, I observed that the samples which are under a constant flow of air, they had less of a peak load. So the bond was weaker, as well as they had less of the fracture energy inside. Although the fracture energy observed in these tests were so, there was a lot of deviation in that. So we can't really conclude about fracture energy here. And then so this that was introduction of damage. Then I let those samples heal in two different conditions each. So these are the samples which were covered previously and then they were healed. So in that as well, we can see that now in terms of water, in terms of water curing, there is a higher strength, and in terms of energy, there is significantly no difference here. And in terms of samples which were exposed to airflow earlier and then they were healed, there we can see that the sodium carbonate curing is performing better for energy as well as for peak load. So in terms of concrete cylinders, we observed that even without damage, sodium carbonate curing was performing better. But in these cases, the difference was not as much, since you understand, if I cure the samples from outside and let the ions flow to the bond, then it's a very less chance of ions getting through to till the bond and then reacting and precipitating something. So that is why the difference in bond strength was not as stark as the difference in compressive or split tensile strength. But we can see that sodium carbonate, if it's introduced in a sample which has been exposed to this airflow or shrinkage or some form of damage, it performs slightly better. And this is the same test. So if uh, this is the bond strength versus age. So again, the same kind of graph. After 1 day, I observe the two. So this is the covered specimens, and this is the uh, this is the evaporated specimens. And among these two, there is a difference. So there is a damage in terms of peak load. And after that, I leave them to cure under different substances. And then there is a similar observation in terms of sodium carbonate performing better, but gain in strength is less as compared to samples subjected to water flow. So here you can see that the difference is lesser in terms of the performance of sodium carbonate in terms of bond strength is lower as compared to other mechanical properties. Again, for fracture energy, it's a similar curve. So basically, again, we can see that if the samples were covered, there is not much difference after curing as well. But if the samples were damaged, there is a difference after curing. So this really shows me that if there is some gaps or some voids or some form of cracks inside the specimens, then sodium carbonate is able to produce that expansive reaction of precipitating calcium carbonate and helping the system gain strength. So that was one technique of inducing damage, which is through a constant flow of air in the early age. And this is the second technique that I use for inducing damage to the samples. In this, I use the dog bone samples and loaded them up till a certain value of area under the curve. So there is a slip that is occurring in the fibers. So after the peak has occurred, I stopped at a certain value of energy, and I stopped at that every time so as to roughly induce the same kind of damage in all of the samples. So adhesive bond basically is destroyed since I load it past the peak, and there is only frictional resistance left inside now. And later they are tested again to see if there is a recovery of some form of bond between the fiber and the matrix. So this is preloading at a certain value of energy. So we can see that after this, this is the preloading and this is after healing. So after healing, there is a difference in between. Again, the sodium carbonate is slightly performing better in terms of fracture energy than this. And this is again for 6 samples each. And then in terms of peak load, we can see that even though the sodium carbonate is performing better than water, the overall peak load is never recovered since once the adhesive bond is broken and it's now weaker in bond, you can never really gain back that sort of a adhesive bond between a fiber and concrete specimen. So this is the same graph again, just the final values of peak load and fracture energy, so as to demonstrate that sodium carbonate is slightly performing better, but there is not much of a significant difference in this case that we can conclude anything from. So if we introduce a slip damage in a fiber, the sodium carbonate is not really able to help. It's performing slightly better than water, but in terms of statistical difference, there is no real statistical difference. So effect of then I tried just in this case directly adding sodium carbonate instead of curing it, directly adding it into the mix. So if I directly add sodium carbonate into the mix, I observe a bad effect on both the peak load as well as the fracture energy. So sodium carbonate, if it's added directly into the system during the mixing process, it starts reacting with A light and B light instead of going for calcium hydroxide. So it inhibits the natural hydration. So that's why we observe a lesser peak load and lesser fracture energy. And this effect is still being evaluated in current experiments that I was doing, and as to how much of sodium carbonate is really bad for this. So this was similar to the split tensile test that I did, and this is just compression instead of the split tensile test. So again, I did the same things. This is just the loading profile that I used in the Baldwin machine in the structures lab. And again, I just loaded it till I just first tested for ultimate strength and then loaded all the samples up to 90% of their strength. And then I removed the load, took out the samples for healing, tested it on that day for damage, and then again after healing I compared those values. So this is roughly a similar test to the split tensile test, but just in compression. And I can also observe the stress strain graph, though this is coming from the machine and not from LVDT that I introduced. So we can see here that in terms of air-based healing, the original had a higher ultimate stress, and after healing, so this is after damage and healing, the strength could not really recover up to that level. In terms of water, the strength was roughly the same, so uh, there was a recovery of the ultimate stress in water after 90% of loading. And in terms of sodium carbonate, it's performed uh, slightly worse off than the original value. So in terms of compressive strength, like we cannot really again say that one is performing better than the other. So after all these tests, I switched to observing recovery of permeability under stress. So this is a setup that was developed in the lab previously. And so what they have is they have a water tank, and we supply air pressure into this tank. This drives this water under a fixed value of pressure, and the water goes into this system. So this is my specimen. This is the hollow cylinder that we can see here. So the hollow cylinder is sealed from the top and from the bottom, and the water fills outside in this zone. So there is water around the sample. And as we pressurize it, the water has to pass through the sample radially inwards, and the water drips out from below, and we can collect that in this in a beaker and measure this weight. This weight, after measurements in computer, we can observe the rise of weight as versus time. So so we can leave one of those samples under stress, or we can have this cell outside without stress as well. So there are two ways that I can approach this test. What I observed while I was doing this test is that compression loading failure in the hollow cylinder is different to the compression failure in any solid cylinder. So in a solid cylinder, we usually observe a shear crack at a 45-degree angle. So there is a conical failure, as you might all know. And in this permeability setup, we load the hollow samples from the top, but the failure mechanism that I found was slightly different. And there is a need to find the correlation between these two values, which I am struggling currently how to correlate these two. So this is uh, so in a solid cylinder, there is just vertical loading, and if there is no eccentricity, there is just compressive stress. There is no other stress there. But in a hollow cylinder, what I found that circumferential stresses arise in this due to basically Poisson behavior, due to the Poisson's ratio. And compressive stress is present since we are loading from the top, but the failure of all of these, when I tried to fail them, they all failed in tension like this. So there is a straight crack going. This shows that there is basically a tensile stress developing inside this cylinder, and this is leading to the failure. So in terms of the ultimate strength, I need to correlate this strength with what we are observing in a normal hollow cylinder when we load a sample up to failure. So in terms of this, I would love to get some ideas on how to correlate these two as to what the failure load in this case will be as compared to the compressive strength case. So in terms of analysis of these permeability setup, what we observe is weight of water that is permeated through the sample versus time. So we roughly get this kind of a curve from the sample. And then to get the permeability, I get the derivatives from this. So from this data, I get all the derivatives. And then from those derivative of permeated water versus time, we can plot a permeability and then use that to create a permeability. This is a permeability distribution. This is a histogram basically to see which permeability is higher. And this we can do for every hour and every minute so that we can compute an average of permeability as the time passes from the sample. We can see that roughly it goes down as the test progresses. So then I wanted to see the effect of pressure on this permeability setup, and the relationship is assumed linear as per the equations of permeability in a hollow cylinder. But um, while I observed the test, there is a lot of scatter in between the values. So we can see that roughly the blue, which is at 90 psi of water pressure, it has higher permeation than 60, and then these two values which are lower. But it's really difficult to observe this just using a permeability measurement. So there is a lot of scatter and a lot of disturbance. What I found while I was doing the experiment is the reason for these scatter is basically the water drops out in droplets from the pipe, and so it's not a continuous drop. It drops out in discrete quantities, and sometimes there is a surface tension inside the pipe which holds back some of the water until there is enough water to go past this tension and like fall in the beaker. So sometimes water drops down in bulk, so that's why sometimes we can see that there is a lot of water coming out. So these are those abrupt values that water drops all at once. And roughly we can see that higher pressure leads to higher permeability. Uh, so what I did was I averaged these permeability values to every hour. And in every hour, we can see that again there are kinks, which is again the high water dropping out all at once. But we can roughly see that again the higher pressure is leading to a higher water flow. This is just the weight of water. Again, we can see that a higher water is leading to a higher water flow. This is a plot of mean permeabilities observed over all the time. So here we can see roughly there is a linear relation. So this we can observe in our experiment as well. So overall mean reflects this increase, but it's not a great measurement since the permeability itself changes over time. So now I wanted to look at the effects of sample loading on permeability. So in terms of effects of sample loading, we can see from this graph, this is the average permeability value. Since we can't really observe this, this is the variation in permeability observed every 10 seconds. So here we can see that this yellow 8,000 pounds value is the lowest. And in terms of this graph, which calculates the hourly average. So here, so these first I compared like for 1 hour all those values, and then I let some of those tests go a long time. So we can see that initially there is a higher permeability with less stress, and as we increase the stress, the permeability goes down, and after a certain value, it rises back up again. So we can see a higher permeability once we go past this value. But I can't really correlate these loads to what is the stress inside, since uh, so what is the basically the tensile stress inside the sample, because these samples, as we have seen before, are failing in tension, not in compression. So in terms of this, this is the plot of mean permeabilities again versus load. We can see that it decreases with load and then it increases again. So it's not monotonic. So there is no a single decrease or increase. And again, the data is scattered because there is a precision issue as well. Let zero point 0.1 gram of water has to flow down for the scale to observe a difference. And then So this is now the test that I did in completion. So what I observed was after 24 hours, so this is 24 hours, the first 24 hours of handling the sample. So we have water inside the system which permeates through, and this is the average permeability with time. So this decreases first faster and then a little bit slower, and this is due to continued hydration that is happening inside the system, that the permeability is decreasing. So this is the first 24 hours. Then what I do is I remove all the water from the system. I replace that with sodium carbonate water, which is saturated up to a 10% uh, by volume. And then I again observe these, again for the next 24 hours, I observe the average permeability in every hour. So from these two, we can see that this one is slightly higher. And even after replacing with sodium carbonate, the permeability goes down and it reduces even to further smaller values. So we can say qualitatively that the sodium carbonate is helping to reduce the permeability even further. But for a real analysis, I really need to, because there are so many values, I really need to make a extrapolation of this and compare that to this curve. So this, I need some more data analysis on this to say things more conclusively in terms of a recovery of permeability. This is something that I've been doing these days. So uh, I tried to model autogenous healing by carbonation and to see if there are some critical parameters that we can find out, and if we can replicate any of these tests using one of these models in Abacus. So in terms of a good autogenous healing model, we should be able to simulate cracking, evaluate the mechanical recovery, and simulate the transport of ions and hydration and healing reactions. So first of all, I have tried these two. So I tried to simulate the transportation of ions through concrete and what impact does it have on a expansive reaction. So I'll not go into much depth of this. This is some literature review that I did for what simulation models that are used. So one is continuum mechanics, which is basically calculates using continuum mechanics equations, what is the damage and what what is the healing. In transport phenomena based models, what we do is we allow ions and reactions to happen, and then healing process can be isolated from the hydration process, and this can be calculated independently. While in the continuum mechanics, since this is a overall energy calculation and this is based on the minimization of total energy, we can't really separate things out in this mechanism. So I prefer to go with the transport phenomena based approach. So this is some paper that I used to understand how we can model self-healing in concrete. So for what I did was I just tried to model the calcium carbonate formation using sodium carbonate, using a carbonate ion and a calcium ion that is present inside. So I'll not go into much depth of what the model is. So roughly currently I'm doing this 1D simulation where I suppose that uh, there is a calcium ion here and there is a crack here. So I assume that there are carbonate ions inside the crack, since it's there in the water as a curing mechanism that I have used in my experiments. So if sodium carbonate is present here, then what has to happen to fill the crack is calcium has to dissolve here, and then it has to travel this length in concrete and reach till the crack. So this, when extrapolated to a, so there are some microstructural models, and I can just introduce these effects inside those, and once I develop this 1D model, I can basically simulate a crack filling procedure by using this reaction. And so this is again into depths of the model that I have created. I'll be happy to answer any questions on this. So I just discretize the space in terms of in one dimension, and then to implement the boundary conditions. The boundary condition is basically on the left side. There is a calcium hydroxide particle that is dissolving, and on the right side there is calcium being reacted and producing calcium carbonate. These are some of the model parameters. And so one observation that I could make for now using this 1D model is assuming the concrete porosity or concrete diffusivity that has been reported in most of the literature. We can see that this is basically the separation between the crack and calcium hydroxide, and this is the percentage of crack filled. So this is basically how much reaction is happening inside the crack. So as we can see, if the separation between calcium hydroxide and the crack which occurs inside the concrete, if it's more than 300 micrometers, there is roughly no contribution of that calcium hydroxide into healing. And if it's close, it contributes to the healing. So there is this decrease in uh, basically decrease in supply of calcium ions from a distance uh, towards healing of a crack. So diffusion coefficient of concrete, if we can calculate it, we can put it into this model for calibration, and then we can basically in one dimension, this shows how much it has contributed. If I do this in a microstructure based system, I can see how much exactly each crack or each void, how much of calcium ion it can get from outside. So this is just a plot of calcium and hydroxide ion within system. So current limitations of this model is that diffusion of water in the pores from crack to calcium hydroxide is not considered. So which had some there was a crack which had some carbonate ions. We have not really considered the carbonate ions going back across and the calcium ions coming at the same time. So I'm working on that part of the simulation right now. And also, if we create a 2D model, so if we can create a 2D model, or we can use other 2D models that come with other microstructure models like HYDE, SEM, or other models, then we can use these equations inside them since they are all in MATLAB and I am also building this model in MATLAB, I can use these equations and integrate them there, and then really see how much each calcium hydroxide is contributing to the crack and where the crack happens. So, and once we can do this in a 2D model, we can also do this in a finite element based Bacchus model. So this is basically the goal, to do a test which is similar to the test that I have done in my testing till now, and be able to simulate those recoveries or the ratio of those recoveries, basically in terms of comparison, and simulate that in a finite element based model. In terms of experimental work that I was doing and which was stopped due to this lockdown, and what we were doing was with Obina was helping me do figure out these testings. So we were trying to determine the amount of sodium carbonate that can be directly added to the system, and see which amount actually causes damage inside the system. So we first tried replacing 0.5% and 1%. We have done these castings already, and 5% we have not done, but these can later be compared with control concrete to see what what is the impact of which percentage of sodium carbonate. And one more method that we would like to introduce sodium carbonate inside the system without causing a damage is to use cellulose fibers to soak up the sodium carbonate solution. So we leave the cellulose fibers soaked in sodium carbonate solution overnight, and then later use them the next day for casting, and then we can test it for verification using the split tensile test or the evaporation test that we did earlier. So this is basically which ends my presentation, and I'll be happy to answer any question.
Thank you. All right, we can open this up for discussion.
And I hope I was coming across okay, because this is the first time I'm doing a virtual presentation.
Yeah, no, it was quite clear actually. We'll open this up for discussion. Any questions for Anupam?
Anupam, I have a question. Why you didn't consider porosity test to evaluate the self-healing? I mean,
So,
yeah, that relate to the permeability as well, or
which kind of porosity test?
That we use with the using that mercury. I mean that the equipment.
Okay, yeah, that I can do, but the issue is I can definitely try that, but the issue was once we introduce some healing or to introduce some damage, and then once we impart mercury or do some porosity test, I need to again leave those samples under different environments and test them again. So while that is something that I can do, if I if I try to figure it out, I think I can do that test. That
Yeah,
should
I
be no
mean,
problem.
I think that would be another evaluation of
One more thing that we wanted to do before the lab was closed was we wanted to test the sorptivity and see how that can introduce a comparison between these samples. So that is also one way that, as you are suggesting, we can quantify the porosity.
Yeah.
Thanks.
Okay.
Hello.
Yeah, Roland, go ahead.
Can you hear me? Yes. Thank you for your presentation. Actually, I have two small questions. The first is about the temperature. And you have mentioned the temperature in your presentation.
Okay.
Do you hear me? And then actually, I think the temperature is very important in the hydration of the cement, and also very important in your later modeling jobs.
Yeah.
So I think this is a very important factor.
Yeah, so the temperature that I have used is I have used the curing room inside the lab. So it's roughly at 23 degrees Celsius, and that is the temperature that I can use for later studies as well.
Okay.
So I have not mentioned it. I should really mention the temperature as well.
So the next question is, actually you have done some many jobs focused on the micro performance, such as the strength, right, and the probability. And I just want to know, have you planned to do some microstructure tests, such as the pore structure? You know, the pore structure is very important to the probability. And
Oh yeah,
I think, yeah. So I think maybe you can have tried to test some pore,
pore structure.
and it's better to understand your different queuing method and some influence factors. Yeah.
Okay. Thanks for the suggestion. Yeah. I'll look into it. Yeah.
That's all.
Thank you.
Any other questions?
Yeah.
Yeah, Shubham.
Thank you for the presentation, Anupam.
Thanks.
So there are a few questions that I need to ask. So basically, you are adding sodium carbonate, like you are soaking your material with sodium carbonate, right?
In terms of the last test in the fibers, in the other ones, I either put them
in the mix.
Curing. Once I use them in the mix just to see what the effect is, but usually I cure the samples in sodium carbonate water, and so it's coming through the water into the system.
So like, have you quantified if any sodium phase reacts with one of the cement hydration phases? Maybe.
Yeah, so that's a real concern. If you have the unhydrated cement and you leave them in sodium carbonate, then that starts to react directly with all the unhydrated particles and affect the hydration.
Yeah. So how are you quantifying that? Like that's a tricky thing actually.
Yeah. So the last test that we were doing is to see what percentage of the sodium carbonate in the slide that is there currently, what percentage actually starts to degrade the performance of the concrete. So if it starts to degrade at like currently that test that I did, I used 5% by volume and tested it for compressive strength. So it led to a huge 40% reduction in compressive strength when I tested it directly. And what I read from literature previously is that the sodium, not the sodium part, the carbonate part itself, it starts reacting with A light and B light in the cement, and that affects the hydration itself. So I'm not really sure about what the sodium ion does, but the carbonate ion itself has a huge degrading effect if it's put in directly into the mix.
Yeah, because I guess like if you are doing all such like just such testing, you need to like quantify how much amount of because that's an important factor.
Yeah.
And also, can you go to slide number 35?
Okay. Yeah.
So so there are two graphs in which one you added it, like you put it in water, and then you dried the powder, and then again you replace that with sodium carbonate water, right? So is the same material or two different?
So let me explain this once again. So there is water inside the system, right?
Yeah.
So this water is what I used for the first 24 hours of observations.
Okay.
And then I removed all this water, like from here as well as from here. And then I put inside the cylinder a saturated sodium carbonate water and use that again for doing the same test with the same sample. So after it has seen a reduced permeability, I use that same sample again and tested it for the next 24 hours under a saturated sodium carbonate water.
Yeah, but how do you know that all the water has been evaporated? Like, have you quantified that, or it just?
No, I literally take out the samples and take out all the water, and then change the water itself. So I don't add sodium carbonate inside the system.
No, like I'm talking about the material. Like you're saying you dried it up to get rid of the water.
Oh, no. I did not dry up the material. So basically that effect, so anyways, like after 1 or 2 hours is when the experiment stabilizes. And after that we take the reading. So I just assume that during that time enough water has passed through the concrete system so as to now be a sodium carbonate saturated system. But you are right that inside the sample itself also there is some water stored.
Yeah, so like to differentiate whether the effect is coming from sodium carbonate addition or the water that was already present and helps in the hydration. So like to quantify that is also tricky here.
Yeah,
Like,
it's tricky. And even in terms of all the results that I observed, there is a lot of scatter and dispersion of the values. So anyways, to analyze the difference is slightly tricky. But in terms of slight reduction in values, I could observe that. But to quantify that, I would need to like interpolate some curve on both of these graphs. And not just these graphs, there is a lot of data inside which I have averaged out and use that for interpolation. But you are right, to quantify the difference, I really need to interpolate these data. Thanks.
thank you.
Okay. Any other questions?
Anupam, Farooq here. Thanks for the presentation. It was a lot of data and very interesting data. I have a little bit of, my question is about the concentration of the sodium carbonate itself.
Okay.
So the sodium carbonate you used was 1 gram per 10 milliliters.
Per 10 milliliters.
And that was constant throughout, right?
Yeah, that was constant throughout.
Do you know what the solubility of sodium carbonate is?
Yeah, so I just wanted to saturate the water itself. So that is, so the solubility is around, I think, 9 grams per 100 ml or around that region. So it's slightly higher than the solubility. Yeah.
So the pond of sodium carbonate you were using, were you trying to agitate it continuously, or did you observe any precipitation in that pond itself?
So once I dissolve it, I don't observe any precipitation like in 1 or 2 hours. But after after leaving the samples under that water for 7 days, I did observe a different color of the samples, as well as I observed some precipitation outside the sample itself. So there was some powder that I could detect, but it did not precipitate like in bulk amounts inside the water. Yeah.
So there wasn't anything, let's say, at the bottom of the pond, for example?
No. There was nothing at the bottom of the pond. So it does not. It does not like.
Yeah. No, I'm just concerned about the atmospheric precipitation, and then if we are losing any sodium carbonate into the atmosphere, or getting reacted.
So yeah, to tackle that, I usually cover them. So it's all in the steel box that I keep all the samples. So there is no evaporation of water happening once the samples are inside.
Yeah, and probably there is no easy way to measure the concentration of sodium carbonate, right, over, let's say, periods of time, to see if any amount is getting used up.
Yeah, because the concentration should really be going down if it's reacting inside the concrete. Yeah, but there is.
But probably compared to the volume that is being used up, the volume of the pond is probably very, very large.
Yeah, it's large. I submerge the samples inside, so it's large than the volume that's being used.
Yeah, those were some of my questions. Thanks.
Okay, thank you.
Thank you.
That's a quick question.
Hi, Suma.
Hi, Anupam. Thanks for the presentation. On the same slide that you're on actually right now, 35, you might have mentioned, I might have missed it, but are these, how old are the samples before these tests? Are they all?
So this is both are at 28 days. So after 28 days, this is the 29th day basically, and this is roughly the 38th day.
So at the 28th day, you put that through, right? Yeah. And then but after 7 days, so they're all going through the 7 days after that, right? Is that?
No, it's 1 day. So this is roughly 24 hours. And this is again roughly 24 hours. So this is like the 29th day is this. And on the 30th day, I change the water.
Oops. I'll try to actually...
I have tried this test in 7th and 14th day as well. But in terms of comparative values, once I redo the test, I take out the samples and put it back in. There is a lot of initial difference after like reloading the sample. So most of the tests that I did, I can't really compare these two values because this used to be turned out in some different domain from this.
Because, you know, the difference is almost like 70-80%, right, between the two. So if you go back to that slide 28 that you were showing, you know, I'm not actually, I've never done this test myself, but the question is, if you take the water, say for example, you have a known molarity on the water that is fed to the system, right?
Yeah.
So say for discussion purposes, if you take that water, like post-test, like after 7 days, and the water that is collected in that beaker, if you take these two waters and compare the molarity of the two, or the concentration,
I understand
I
the
don't know if there's a
concentration of the
way,
two,
how
or
much
the
of a
pH
loss
as
do
well.
you have?
But this the water that comes out is usually up to 50 or 70 grams, not more than that. The water that eventually comes out in 1 day, it's roughly around 50 to 70 grams of water.
Yeah, but how much of the sodium?
So it's all the water when I use sodium carbonate, it's at 1 gram per 10 ml.
Yeah, but if I ask you, the water in that beaker is that like
it at the same
0.5 gram
concentration
per liter, or?
Yeah, so for that we have to measure like the concentration of sodium carbonate inside water, concentration of carbonate ions.
But
Basically.
would that give you any information or quantify what the Shubham, for
Yeah,
example,
it should give a difference, because if the carbonate ions are getting reacted in the system, then this should have less of those carbonate ions. So
but
there
in
should
order
be
to
a
quantify if that's
for
if
that
that's
we have
coming
to
from your
measure
hydration, or
for that we have to measure the concentration inside here and here as well. Yeah, that can be used as a comparison. Yeah.
Thank you.
Hello, Anupam.
Hi, Abhinav.
Thank you for the presentation. I think at this point, we need suggestions on very simple things we can actually do in addition to what you've done.
Yeah.
If anybody has any suggestion to make, because we don't have luxury of time anymore.
Yeah, and even the
before we left, I was actually thinking if we can bring in some quick non-destructive texting to combine, like when we split the sample, partially preload the sample under splitting tension, then you do your self-healing. Before you start the self-healing, we can actually use our UPV to see, have a baseline. Then you do your self-healing. Maybe on daily basis, we can, because if we plan it very well, we have one crack at the middle of your sample.
Yes.
If there's healing going on, sending an ultrasonic pulse wave from one end of the crack to the other, which should actually give us an indication that if you are having a healing or if you're not. That's something easy and fast we can do in addition to the subjectivity test we are planning.
Yeah.
Because this permeability test is a whole lot of work, and there's a lot of variables here.
Yeah.
So I'm thinking if we look at something simple, we can wrap up this thing as soon as possible.
Yeah, really. So while doing this test, I can do what you are suggesting as well, along with these tests. But the lab has to open for that, right?
Well, meanwhile, like I told you, I think on Monday, what you need to do is start writing the chapters.
Yes,
So
I've been doing that. Yeah.
Yeah, we know if the chapters are completely done, we know that it's just a question of additional tests.
Yes.
Hopefully, we should get something out of it. Then we call it a day.
Yeah. Thanks, Obina. Yeah, I'll do that. I'll do that definitely.
Hi, Anupam. This is Anurag.
Hi, Anurag.
Yeah. So the information was the presentation was very informative.
Yes.
I just want you to shed some light on the scatter, the huge scatter of the permeability data that I think it was in slide number 30, 31, something around
Okay,
that.
yeah. I
think I couldn't follow that. So please, can you shed some light on that?
Okay, so this slide, right?
Yeah. This one.
Okay, so basically what I wanted to say was that we can observe overall a reducing trend of permeability, but there is a lot of scatter in these values. So the reason for this scatter, from what I figured out during the experiment, is since the water comes out through this pipe from below the system, this is not really vertical. It goes like this outside into the beaker.
Okay.
So there is a resistance of water flowing down. If the amount of water flowing down is very small, there is a resistance to the water dropping inside.
Okay.
So what happens is some water. So there, first of all, there are drops that fall, and sometimes those drops collect and they fall all at once.
Okay.
So what it does is it affects the scale, and the readings go up and down for some time, and then we observe a straight reading again, and then so that's why there is a lot of dispersion. And even in this one, we can see that there is a basically there are some discrete values. So what happens is when the water falls down, and there is a stress introduced into the system, and what happens is the scale it starts going up and down. So also, since the precision of the scale is 0.1 gram, so that much water has to fall for it to record anything. So we can see from this one is that what happens is it first goes down and then goes back up. So uh, that's why there is a lot of scatter in the system.
So from
Plus
this,
there are some disturbances from outside as well, I think, which affect this. So if something happens in the lab during this time, it might affect the values as well.
Okay, so from this scattered data, you averaged out to obtain the data that is shown in the next slide.
Yeah, this is so averaged every hour. So for each hour, I average all the
peaks, or just all the data.
Average all the data inside.
Okay.
Yeah. And what I do also was I calculate basically. So this is the first derivative, right?
Okay.
So I also calculate the second derivative of this, and so basically to clean this, I remove some very high curvature points. So if there is a very high curvature, then
also which is changing the nature of the graph, so you just drop that.
Yeah. So if there is like a peak in this, or if there is a kink here, then I remove specifically that point.
Okay.
Yeah.
And the next thing was you said something about the you couldn't conclude something about the fracture energy. If you could shed again some light on that. Yeah, sure. I don't remember in which slide it was.
So in this one, or I think this one, right? Yeah, this one was it.
Yeah.
So in terms of what I could conclude was, I said when I test these samples again and again, there is a lot of dispersion. There is a lot of scatter in the values of fracture energy. So you can see here that the energy is scattered all across this domain.
Okay.
And same with here. So you can see the scatter in peak load is lesser than the scatter in energy, and even in pullouts to test, as I think you have done that. So you can see that there are a lot of difference in values from sample to sample as well. But in terms of energy, it's even more, the difference in values.
Oh, so the energy scatters more.
Yeah, that is why even if I do like 10 samples of each, there is still a lot of scatter, and so that's why we can't really conclude
something.
Things about the fracture energy here. Yeah.
Okay, thank you for clearing my doubt. It was a nice presentation.
Thanks, Anurag.
And a quick question, did you measure the numbers by hand or is it a data logger you have at the scale now?
So it's we modified the Simon helped me to modify the program, the program for pull-out test, and what he did was he plotted. He showed me the area under the curve on the screen.
Oh yeah,
So I
no,
could
I was
see.
actually talking about the
Okay,
permeability data.
okay,
Sorry, I didn't
sure.
clarify.
Okay, sorry.
On
Which
page
one? This one?
28, yeah.
Yeah.
Just out of curiosity, did you? So there is a data logging for it, right now?
Yeah. There is a data logging. So
MASc.
there is a scale here. Yeah.
MASc. Okay, Shubham.
Yeah. Anupam, I saw in some of your slides that you sometimes you like you use fan to cure the samples, and sometimes
Yeah, no, so no, it's not to cure, it's basically to subject them to a constant flow. So what I did was the fan was a rotating fan. So in that domain, I spread around the samples at a certain distance. So the fan was going on for like 48 hours or 24 hours, and it was putting all those samples under a constant flow of air. So
yeah,
if
but
we do that in the very early age of concrete, it affects the hydration and it evaporates some of the water from inside and damages the sample.
yeah. So my question comes there. So so if you are using fan for some cases, so there are a few slides in which
Yeah, I can go back to that. Yeah, sure. Yeah, so basically this was it. Yeah.
Okay, yeah. So I see that in some of them you use fan with different components, and one was covered with different components, right?
Yeah.
So unless you know the amount of water that was present even after evaporation,
Yeah.
right? And after that you cured, and so my thing is unless you like again quantify these things,
These
it will
things,
be
yeah.
very hard to know whether it's coming from
Yeah,
water
I know.
heating or
And
sodium
yeah,
carbonate.
I was trying to think of a way to figure this out as
Yeah,
to
yeah, and
so
all your testing depends on this because you
yeah.
need to show what is affecting your final system, right? So this remains an important criteria, I guess, for you to quantify that. Yeah.
But in this case, like both were dry, but still, yeah, we need to figure out what is the loss of water
Yeah.
from evaporation. Yeah. But if
Thank
there
you.
is a way to do that, like if anyone of you can suggest while doing the test this time, I can just use that criteria. Just asking for any suggestion at this time.
Maybe initially check for water loss, like the weight of
The
the
weight loss,
sample.
I did check the weight loss, so
Yeah, so
I
like
should
kind of like try to relate that, but that's not like really specific. Other way, I can't think of that way actually. Yeah. So for now that, but I can think of it and suggest you something if something comes
yeah,
up.
sure. I'll be happy to
Yeah.
go back on this. Thanks, Shubham.
Okay. Any more questions?
Anupam, just a couple more things.
Yeah,
you indicated that you were going to do some more sorptivity tests, right?
yeah.
And that would be on cylinders that have been split or subjected to some
Yeah.
stress?
Yeah, up to, so they have been preloaded and then loaded till like 90% of the sorptivity. And then after that, so I am expecting to observe some differences between the preloaded samples and the original samples. And then after that, after putting them into different healing conditions and drying them again, then again I'll do the sorptivity test without loading this time. So
Right.
that's when, yeah, I can see that.
Yeah. Yeah. So basically, the sorptivity is going to change if there is a crack, right? And
Yeah.
if the crack starts to get filled. But if the crack is a little too wide, then the water will not rise up because there won't be enough surface tension.
Okay.
If that single crack is too wide, then we won't see any difference in sorptivity.
Yeah. So yeah, to go back on this, so while Obina was suggesting this, so there are internal cracks inside the concrete. There is no single crack that is like very wide, while we are below the ultimate strength. So what I'm expecting is the cracks inside, the internal cracks are fine enough for like this activity to be affected. And Obina showed me some previous results that once the samples are loaded to these values, they do see some differences in activity. Yeah.
So let me come in. I have done something similar to this in the past. So it actually works. So the problem is, will the sodium carbonate we are bringing in be enough to make a difference? That's where we are stuck. But the test method, it works. I've seen it. But the thing is, we are not sure really what amount is the optimal to induce self-healing. So that's the main problem we are having. In fact, all the tests he's done, he's doing external curing. But the whole idea, the practical thing is actually to come up with a system that you actually have self-healing. Because what we have now is external curing with sodium carbonate, which in reality is not even practical.
Yeah.
So our main problem right now is how do we bring the ideal amount of sodium carbonate into the system and get self-healing going? That's the challenge we are having.
Yeah, some kind of micro encapsulation.
And that's what the fiber was supposed to do.
Yeah, exactly.
Yeah, but the thing is, we need to do some trials to be able to, figure out. We have different types of the cellulose fiber. We figure out which one actually will work better. Because with the cellulose fiber, there's another problem. I don't want to go there, because the cellulose fiber doesn't like alkaline environment. So now we are bringing in, using the cellulose material to soak up an alkaline solution. So it might, if hopefully it works, on the long term, we might end up losing the cellulose fiber itself. So the only hope I'm having is we have one particular type of cellulose fiber that will not have this degradation problem. Namely, that's the PBF. So I'm thinking worst case scenario, if we have a positive development with the cellulose fiber, if degradation is an issue, we can fall back on the PBF because of the refining, the lumen has been removed. So it doesn't have that problem compared to the regular microcellulose fiber. But at this point, it's still all conjectures because we are not sure if the amount of cellulose fiber we are using can actually bring enough of the sodium carbonate. We started at a small amount. I think, Anupam, how many percent? Okay, 0.5%.
0.5% is what we started off, yeah.
That brings in about, I think, 72 grams.
72 grams, yeah.
Of sodium carbonate.
Yeah.
That's a lot.
The problem is we are thinking let's start small, gradually scale up until we hit the plateau where the sodium carbonate does not affect your strength anymore. So that's what they're thinking. The thinking is if we gradually scale up, bringing small dosages to the point where we don't see any drop in strength. Hopefully, then at that point, the self-healing can take place. Because what from the previous result he's shown, if you just bring in any amount above the optimum, right from the beginning, you lose your whole strength and microstructure. There's no self-healing you can do to get back to your normal. So the point is, if we can be able to figure out the exact dosage that we avoid losing strength from the start point, then I think we'll be able to figure out something.
Obina? You said the cellulose fibers don't like the alkali environment, so
they don't.
Do you expect any, you getting any? Are you talking about the toughness added by the cellulose fiber, or are you talking about something else? Like what? How is it damaged? Like
it starts degrading. So when calcium hydroxide and any alkaline solution is entrapped inside the lumen, which is inside the cell at the middle, so it kind of embrittles the fibrils.
Okay,
so the kind of
absorption capacity will be affected in that case. Then. That's the damage, right?
Yes.
Yeah. Okay. So just a quick, what if you have an oven dry, for example, cellulose fiber, you soak it with the calcium hydroxide solution, and then you make them oven dry again, just for discussion purposes. Would that still, without any moisture present, would that be a solution to just keep, like, for other ways of infusing that calcium chloride inside the fibers without damaging them? Is that one way of doing it, or no?
Well, this material has a lot of issues. Drying it, we call it, if you dry cellulose fiber, then you want to soak, there's what is called honification. So it doesn't swell as much as you want it to swell again.
Mm-hmm.
So that's another issue. But at this point, the plan is to try the different types we have. We understood how it works and see which one will be most suitable. That's at the point we are now. Well, everything depends on when we can get back to work.
Sure. Let me come in here with some reality check here for you. So there's a lot of tests here. I mean, we can keep making plans, I think, as to where we want to go. But I know in real life, perhaps we may not have those chances. So I think we have to work with what you have. We can make all kinds of plans, but there's a lot of tests here, clearly. But a lot of these tests also have a lot of questions. What I'd like to see is, in fact, what's salvageable, I think, in terms of really demonstrating what you're trying to demonstrate here, right? So bond slip test, somehow there are many questions, I think, in terms of really the procedures, in terms of really what you tried to do and what you actually were able to do. Variability in these tests is very high, as we know. So I think it's very hard to even tell whether a specific testing regime is even helping. Water content, as Shubham said, these are a bunch of questions I don't know. So think about if you were to publish these data ever, how many reviewers would come back and actually be on your throat telling you that these are all the questions that we have not even answered, right? So I don't know what the certainty of that is. So if you look at even broadly what you have done, Anupam, I think to me, what seems like is the permeability work is the one that perhaps has got some merit here. I was a little bit surprised by the fact that you said you need 90% stress to create damage and compression. I really find that quite surprising, because if you look at previous permeability work, I think you are introducing damage, some post-structural damage at 30%. As you know, I mean, the typical curves are...
Nemi, so that was not to introduce damage in permeability, that was to introduce damage in compression.
I know that.
In terms of permeability, that's not the case.
I know that, but I think the damage is damage for me.
Okay.
And I don't know if you can count one damage for one, set of kind of exposure versus another set of exposure. Normally, we do know that the moment your curve has become nonlinear, which is at approximately 30%, there is some internal damage that is already taking place, regardless of whether you're able to detect it or not in your test. That's a different question. So that becomes, in fact, a test variable for me. You would often and always see, unless it's really a UHPC, where you have a 200 MPa concrete, you probably will see damages at about 50% and above because of your very good bond. But in the concretes you're testing, I would have thought that I think the damage is created approximately at 30%. But let's go on your permeability plots, where you have this massive variability. So we need to salvage the permeability and just understand really what this is. First of all, telling you that, yeah, the next one actually.
Okay.
Next one after this, yeah. Actually, I like this plot a lot.
Okay.
Anybody who has done permeability work, and we've done thousands of those, to get, in fact, even a good sense of that middle ground, where is approximately 1.5, 10 to the power minus 11 meters per second, which is showing you that indeed this is really what the representative permeability is very good. And the fact that you get a higher permeability because of higher flow rate is most likely because you don't have equilibrium in these tests. Now, permeability is supposed to be a material property. What that means is your input pressure, which is really what you're looking at, 98 psi is your input pressure, right?
Yeah.
So to produce, in fact, a greater permeability at higher input pressure, that tells you that, in fact, you don't have equilibrium in these tests. Normally, you shouldn't see that, actually. If you have, input equal to output, you should really get one. It will be variable, but within the same PSI value, you will see a lot of variation. But that variation would not be tied to your input pressure. That's what I'm saying. It should generally be if you have equilibrium, you should never see, unless your pressures are so high. And I do see that I think your pressures are so high here that you're probably at 90 psi pressure, you're actually damaging the microstructure.
Okay.
Yeah. So, if you have, what's 90 psi in megapascal? So it's just about 1 MPa, right?
Yeah, it's about
in that range, actually.
Yeah.
Yeah, so you're sort of in the range of your tensile strength here, literally.
Okay.
What that means is there's probably is a reason other than equilibrium. You probably are damaging the microstructure as a result of very high pressure. Most of the permeability work, we do it as something like 10 psi, as you know, right?
Okay.
So that you're not actually damaging the microstructure through that very high pressured water going through your pore structure. So that may be one of the reasons why you see this higher permeability at very high sort of input pressures. That should have been lowered. So let's go to your. So this plot is okay. I'm not as bothered by variability in these tests as I normally would be in a permeability test where you see huge variability in data. One order of magnitude is very common, even in the same test, even in the same pressure range. One order of magnitude is very good. So not seeing that here, I think, is I'm kind of comfortable, basically with that. So maybe that equilibrium pressure or equilibrium test, which you're not running, probably is one of the reasons. And second is maybe pore blocking. You always see, if you go to the next plot, one after this, one after. So this is the mother of all plots for me, where question number 1, do you have pressure here on your concrete?
In this one, yeah, there is 10,000 pounds of load on the system in both the cases.
So what's that PSI? What's the stress in the material?
The stress in terms of compressive stress is about 10 MPa, about 10 MPa. But in terms of that stress that I was talking about, that opening of the splitting tensile stress, that I couldn't figure out, like, what is that?
You don't need to. You don't need to. Concrete never fails in compression. It always fails in tension. So even when you run a cylinder test, your failure is always in tension. So I am not worried about that there is tensile stresses on your wall, because there is always the failure stresses which are tensile, even in any compression test. So let's not worry about the stress distribution. Nominally, your principal stresses are compressive here, which is all I care about at this point. I don't even know what the stress distribution is, perhaps. But I think you worry about your principal stresses here, which is indeed in compression. Sure. So it's about 10 MPa, you said, for us. For a material, for a 40 MPa concrete, right?
No, the strength of concrete that I tested was around 30 MPa, not 40.
So 30. So you're just about at the cusp of noticing a change in permeability as a result of stress. Because, you know, up to 30%, you'll generally see a pore compression. So, you know, as you go from, say, 0% stress to 30% stress, and that's been published by many people, you will see that there is generally a compression, a pore compression, which your permeability starts to decrease, you know, under that. And then at about 30%, you start to actually see the increase, which you saw as well, right? I mean, in your curves, you see.
This one, I saw that.
Show me which curve is you pointing at here.
So, in this one. So plot of mean permeabilities. Oh, I said it's pressure, it's actually load. So this is like with increasing load,
yeah,
you have the mean permeability.
Right. So when you convert that to stress per meter in concrete, that's your load.
Yeah.
So
this is around 10 MPa here.
So that's approximately 30% approximately of your compressive strength.
Yeah.
Oh wow, that makes sense now.
Yeah.
Okay, it's about 30%. You start to actually see an increased value of permeability. Okay, so this is very well known. So you're actually replotting everything that's been done by many other researchers before.
Okay.
That up to 30% you see pore compression, which is what you see.
Okay.
And then you start seeing actually an increase in in the permeability. So it's perfect. But I go to your next plot now. Are there parallel plots here that you have for an increased pressure or increased stress in the cylinder?
I do have them. It's just that once I unload everything and I reload the sample again, usually in this one, I got a similar sort of permeability. Usually I get a different permeability the next time I load it. So that's why I can analyze those as well, but there are not, like, we can't really compare one graph to the other graph.
Right.
We can only compare through the graph, like what is happening.
Do you have the data beyond 20 hours?
Yeah, I have like up to 7 days of data.
All right. So does it kind of level off?
Yeah, it does level off. After
Okay, so that's your okay. All right, perfect. So that's your value of permeability, because what you're looking here is pore blocking. So you know, as you move water through the system, what happens is a lot of, you know, sort of internal distribution takes place, where you have calcium hydroxide is actually moving, which is a soluble component. You start getting pores that are starting to get blocked through the process, and this is very well known. And so after a point, I think after this 20 hours, if the curve starts to become level off,
it does start to level off.
perfect. So that's your real value of permeability. I would actually ignore this initial part of the curve.
I understand.
That's your real permeability, is when you are then running the test in an equilibrium way. Okay. Now, if I look at that value of permeability, where the plots have actually, you know, flattened, or it's actually giving a stable value at several different levels of stress.
Okay.
That's what will indicate to me if there is anything going on in the healing side. This doesn't tell me anything, because yes, I see, you know, there is a little bit of a drop in initial permeability because of your sodium carbonate there, but you're still in the non-equilibrium region there.
Yeah.
So I wouldn't take this data to market at all. Because that's what it's telling you, is that there is in fact a different rate at which your two systems are equilibrating themselves.
Okay. Yeah.
You see what I'm saying?
Yeah, I understand. This is the transition zone.
This is really, this is all an artifact, I think, that in a test that you're actually slowly equilibrating your specimen to a point where the inflow becomes outflow, and your permeability becomes, constant, right? I don't know if you have seen a paper we published many years ago, where we circle when we reverse the flow a couple of times. Have you seen that paper? Where we reverse the flow a couple of times, and when you reverse the flow, you attain equilibrium much faster. Anyway, so what it's telling you is that when you reverse the flow, you start actually getting an equilibrium which comes out much faster in your system itself, right? So what you need to show me is not these plots, which don't tell me anything at this point. What you need to show me the equilibrium plots, and compare your equilibrium plots at different levels of applied stress with and without sodium carbonate.
Okay, I understand now.
That's the only way you can show that there is any internal healing going on in this system.
Okay. Yeah.
Okay.
I do have the data. It was so dispersed, so I removed that part. Okay. Yeah, I can do that definitely. I do have that data. I just need to
All
put
right. So
that in the class.
let's take a look at this. I mean, this is all interesting, and it's actually following very much, I think, what I would have expected, really,
Okay.
for your systems to do. But you can't look at these plots and say the sodium carbonate is doing anything. What you can simply say is sodium carbonate is actually helping you get that pore blocking much faster here. It's blocking your pores rather than curing your system.
Okay, I understand.
Which is in a kind of a roundabout way, it is actually self-healing or self-curing, but it's really not conclusive for me at all until you show me what's happening at different stress levels.
Okay, sure.
Okay.
Yeah,
so plot those,
as
know,
well,
and then we can take a look at it. One last quick question. I think I know you love modeling, and I like that. I think modeling is always fun. But you're doing this modeling to predict what specific property? Is it for permeability? Is it for strength? What is the end goal here?
So the end goal is to be able to use this modeling equations that I have done in 1D, and use them in a FE model. So there is a process by which I can introduce these reactions in there.
Okay.
And do the normal testing that I do, which as in Abacus or in other finite element models, you can replicate those tests. I will give the properties as a program to the system, and then we can hopefully
Can you predict permeability based on these?
Yeah, definitely. I have made one program to predict permeability as well.
Okay, that's good. That's what I'd like to see, actually.
Yeah, that's we can do.
Okay. Very good.